Continuing on with some vocabulary from chapter 9. Inductive reasoning. Today we're gonna learn inductive reasoning and deductive reasoning. Okay? Hit pause, write this down, or maybe wait till I finish talking and then write down. Let me paraphrase. It's up to you. So inductive reasoning is when you find a pattern and then write the conjecture for the general case. So inductive reasoning is based on patterns. Okay, that's the key to inductive reasoning. It's all about patterns, and then you can write your conjecture and your rule and all that good stuff. So here we have three figures. We need to figure out what's the pattern. Okay, so in this case we have half of it yellow. Here we have 1/4 of it yellow, or orange or cream or whatever you want to call that color. And here we have 1/6 of it colored. Okay? So what part do you think is going to be colored in the next sketch? Okay? Well, look at what's happening in our pattern here. Looks like we're probably going to have a 1 on the top, right? And then here we're going up 2, 4, 6, well, 8, right? Who do you appreciate? So our next sketch would have 8, and one of them would be drawn in. Okay? So here we have an example. It's a little bit less fun. Okay? So it tells us that the numbers such as 3, 4, and 5 are called consecutive integers. Okay, so would be like 10, 11, 12, right? So make and test a conjecture about the sum, so adding up, right, of any 3 consecutive integers. Okay, so what we need to do is see what happens. So if we add, remember sum is adding, right? So if we add 3, 4, and 5, 3 plus 4 plus 5 equals 7 plus 5 equals 12, right? So if we were in class, I would say, okay, somebody give me 3 more numbers, or I'd say, you give me 3, anyway. So I'm just going to try a couple for you. So 10 plus 11 plus 12, those are consecutive, right? Would give us 21, 33. Okay. I should probably use calculators to double check. I'm sure I'm right? 10 plus 11 plus 12, yes, equals 33. Was I right at 3 plus 4 plus 5 equals 12, okay? What else? How about 33 plus 34 plus 35? Use some big numbers. 33 plus 34 plus 35 equals 102. Okay, well, let's see. That's even, that's odd, that's even, so that doesn't really mean anything. Okay. Well, how about well, you know what's true is that if we add up these numbers every time this number is bigger, right? Okay. So our conjecture could be that if you add 3 consecutive integers, then you will get a larger number, something like that, okay? The point being that you need to test at least 3, okay, and see if you can figure out. You might need to keep going, test a few more to figure it out, okay? But that's what it means when we say make and test a conjecture, okay? So, the counter example is kind of a big deal, okay? So make sure you write this down. Not that you wouldn't, right? So the counter example is what we use to say, no, that's not true, okay? You only need one counter example. If one thing says that your conjecture is false, then it's false, period. You only need one example. And there might only be one example. There could be, though, a gazillion counterexamples. Okay, so let's see what. Let me show you what. Write this down. Pause. Write it down. So, here's the conjecture. Okay, the sum of two numbers is always more than the greater number. Okay, so test it. See what you can come up with. 2 plus 5 equals 7. So the sum is bigger than the greater number. That is true. Okay. This is not very specific. It just says numbers, right? So what if we did 2 plus negative 5? We would get negative 3. Is negative 3 bigger than negative 5? Oh, it is, isn't it? Okay. What if we did, I'm running out of room, negative 2 plus 5 equals 3. Is 3 bigger than 5? Uh-oh. So that is our counterexample. Now, you might have picked negative 1 plus 4 equals 3, right? Not a true statement. So that might be your counterexample. One of the fun things about counterexamples is that we can all have different counterexamples. So it makes it very difficult for me to test you on this because everybody's answer could be different and all be correct too. So that's counterexamples. And I think, oh no, I have more. Okay, so deductive reasoning. Remember that inductive reasoning uses patterns, right? Well, deductive reasoning uses facts, okay? So inductive reasoning is patterns, deductive reasoning uses facts, information that we know to be true, okay? So we're gonna look at a couple of examples. So each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up in the air, we're going to assume it's going to return to the ground. Is that patterns or is that a fact? Well, it's just a pattern, right? She's kicking the ball up in the air. That's not a fact that it's going to return to the ground. Now, some of you are saying, yes, it is because it's gravity. But she could kick the ball into the air and it could end up in the neighbor's yard, right? So it's not really, it's a pattern that's what's happening, okay? So that would be inductive. Now, all reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. Well, the fact that reptiles are cold-blooded and parrots are not, those are facts. That's scientific, that some science person figured out, right? And so this would be deductive reasoning. Hope that makes sense. That's all I have. I will see you in class to work on your assignment.